So today we are going to learn how to draw the axial load diagram for the axial loading bar like this. So the first thing we are going to do is trying to, whenever we had a load change, let's try to draw a vertical line so that your axial load diagram is going to be according with your structure. And then we are going to draw a horizontal line to represent the zero. And normally we are going to put the tension first above the zero line and compression below. And then what you have to do before you do any drawings, make sure you give the name for each diagram. So now what we are going to do is actually do cut. So let's try to do a cut between A and B so that you are going to see you can flip your card or your paper and then decide which side you are going to pick as your FBD. Obviously, we are going to pick the right-hand side as our FBD because we had less load. And then when you draw the FBD, you will see, in order to balance the 10 kilonewton external loads, we need to have our internal force going this way to balance that. And this is compression, not tension, so which means we are going to draw it below the blue line. And you can see, you can move your card a little bit. You can see there's nothing change. Only the length will change on your FBD, but your internal force will remain the 10. So that's why we are going to have a straight horizontal line. And then if you can keep moving your cut, you can see now, once we pass the point B, we are going to involve more loads. So which means our FBD will change. So this time, the internal force will be still compression, but become a little bit less, which means our axial load diagram will be drawn like. And again, what you're going to do is try to keep moving your card. I'm not going to draw the FBD, and then you do your own count. And we can see our internal force will change to -6. And then if you keep moving your card, passing through D location, we are going to have, and this is going to be your axial load diagram. So you're probably going to ask me, between D and F, why you still choose right-hand side as your FBD? You had that many load. Why you didn't choose left-hand side as your FBD? The reason is because the fixed end, you have to calculate the reaction force. If your reaction force calculation was wrong or you forget about this force, then your axial load diagram will be wrong and your arrow will be carried on. So that's why I highly recommend you every time try to use the free end, which is no support, as your FBD to draw the axial load diagram. So let's see the different one. So now it's going to be the same knowledge. We are going to do the cut and we keep moving our cut. So what is the difference you can see is here, that we are going to have more and more arrows kind of involved. So what does this mean? It means that the more arrows here is actually going to be a distributed axial load. So which means you are going to see some units, and the units can help you identify the load. So when you move your cut, you can see we had more and more arrows involved, which means we're not going to have the straight horizontal line anymore. We're actually going to have a sloped line for the axial load diagram. And the slope is going to be equals to the distributed load magnitude. So we are going to start from the free end. You can see if we cut at the zero length, the internal force will be a tension 4 kilonewton. And then you can see if you are moving the cut, more and more axial load will be involved. And it's all in the tension direction, so that's why we are going to have the internal axial load will increase. So if we multiply 0.9 meter, eventually we are going to have 4.9 kilonewton. So how we are going to link this? We have to use a looped line to link them together. And then after we pass in the 8 kilonewton, you can see our force are going to jump to the new value of 0.9. And then you can see they're still in the tension direction, so which means finally we are going to have more tension force, and this is going to be your axial load diagram.